Hello, my name is Fengyuan. I'm a postdoctoral researcher from University of Glasgow. Now I will present the study on the gate capacitance in the double nanowire-based field effect transistors. So the first is the introduction section. Nanowire is a promising building block for high performance, flexible, and printed electronics. And to study the nanowire-based FET, one important aspect is to study the nanowire-based to study the gate capacitance of the nanowire-based FET. Previous study mainly focused on the study of single nanowire-based FET, and but in the real cases, it may be far more complicated than that. So this study is one step towards a more complicated nanowire-based FET. So this study presents the double nanowire cases, and I think, but still, this is an important step if we want to study more nanowire-based FET or completely random nanowire-based network-based FET. So the method we use in this study is two ways. The first method we use is console simulation. And then we also compared with the analytical method, which is the classic cylinder or plate model we use to calculate the gate capacitance of the entire system. But the analytical model is only used for single nanowire scenario and compared with the console simulation. And for the much more complicated double nanowire scenario, there is only console simulation results. So let's go to figure 1. Figure 1 shows the single nanowire-based FET, and it is further categorized into two main parts. The first part is the we call it embedded case, which means that the nanowire is embedded in a uniform dielectric layers as shown in the figure here. And the other type is called non-embedded case, which means nanowire is mostly floating in the air except from the bottom surface, which is in contact with the bottom gate dielectrics. And underneath the bottom gate dielectrics is the gate metal, so which we use to give the bias, gate bias to the entire system. And yes, the results is shown here. As so there are two parameters here. One is T and the other is R. T denotes the distance between the center of the nanowire to the underlying gate metal, and R denotes to the radius of the nanowire. So the ratio of T versus R means how far or how close the nanowire is with respect to the gate metal we use to for the gate bias. And the results are shown here. As you can see, the larger of the T versus R, the smaller of the total capacitance of the entire system. And in the meantime, if we increase the radius of the nanowire, the total capacitance of the system will be increased. So then we move to the double nanowire scenario. And for double nanowire scenario, we discuss it in two parts. The first part is in the 2D case, which means that the two nanowire are always parallel. And as shown in the schema here. And in this case, the increase of the nanowire to nanowire spacing will lead to a significant increase of the total capacitance of the entire system, which means this is because The existence of one nanowire will lead to some screening effect to the electrical field to the other nanowire. So that increase of the spacing between two means the screening effect will decrease. And in the extreme cases, when the two nanowire are quite far enough from each other, then the entire capacitance is more or less equals to the double value of the gate capacitance from single nanowire FET. And another extreme that is that the two nanowire are very close. Then in this case, it is more. It behaves more like a thin film rather than nanowire. And then we consider the 3D case, which the results shown in Figure 3. So basically, there are three parameters here. We can define the double nanowire system in a 3D way. So the factor G and theta corresponds to the relationship of the nanowire center to center. So G corresponds to the center to center distance, and theta corresponds to the relative angle of the center to center. And so basically we have a reference line here. So this nanowire will always be staying in this way. And the change of the theta here will lead to the change of the center of the nanowire with respect to this reference line. And in the meantime, we also need to consider the relative orientation between the two nanowires, so which is quantified by the sigma here. So it means that this means, so this nanowire will be always be staying like this. And the sigma quantify the relative orientation between this nanowire and this nanowire. Okay, so let's go for the results. For the results, we first study the impact of the nanowire to nanowire distance G. So we fix the G equals to 3 micron. And in this case, as you can see, the change of the two angle sigma and theta will not lead to a big change for the total capacitance of the entire system. And by contrast, if we fix the if we change, let's say we change the nanowire to nanowire distance G, and we can see some different results as can be shown here. When the G is small, then in this scenario, the relative orientation between two nanowire would play a significant role here. The change of the relative orientation of the two nanowire will lead to almost 1/3 of the change of the total capacitance. And by contrast, if G is very large, means let's say G equals to 2 micron, and in this case, the change of the relative orientation of the nanowire will not lead to a significant change in terms of the total capacitance. So that is the conclusion of the entire study. If you have any questions, feel free to let me know.